This afternoon we have a very interesting presentation from Matthew Archer, who is the Technical Product Specialist at Audio-Technica. It's entitled Don't Drop the Ball, and it's about the successful implementation of wireless microphones in live sports broadcasting. I think this is going to be a very interesting presentation, so over to you, Matthew.
Thank you. So as he said, today is mainly going to be looking at wireless systems as a whole, and we're going to focus on a sports event when we actually look at specification, and the aim is that we all go away with some ideas of what might have been causing a problem in our setup, little things that we might find that we wouldn't have considered that have actually been causing us a particular issue. So obviously, in 45 minutes, we only get a very glimpse of things like what goes into a sports event. I mean, a sports event takes around years, depending on the complexity and the price involved in that project. So going on to what we'll actually be looking at. So like I say, we're aiming for 45 minutes. We'll see how we get on. And so we're going to have a look at wireless audio technology as a whole. So I'm quite aware that we have quite a broad range of people here today. So we'll be looking at the technologies as a whole, looking at benefits of certain systems, what we think, what other manufacturers think. And then we'll go through an example specification from an event that Audio-Technica have done most recently. And then we're going to pull out with that information that we think is going to help you in a project that we might not have considered before. Okay. So as we said, my name is Matthew Archer. I'm one of 6 other technical product specialists in Audio-Technica. It started out as 1, it became 2, it became 6. One of them used to do it, sat right there. We've grown quite a lot as a company, and we also distribute other brands as well that we support as well. As you saw at the stand, we've got Allen Heath, A-Part, and there's another company called Art Novian as well. But we are Audio-Technica as a manufacturer, and in the UK we distribute those. Okay. So yeah, like we say, in terms of Audio-Technica ourselves, we've provided microphones for sporting events for a very long time, including the Summer and Winter Games, which we've supported since 1992. And that's exclusively that all the sounds of what we hear in an event in the Summer and Winter Games are Audio-Technica mics. Obviously, I'm not referring to the BBC's broadcaster mic and things like that. We're talking about sounds in the games when we hear that. And there's a few pictures to give you an idea of what I mean by Summer and Winter Games. And then, so the first half, as it were, so it's mainly going to be half on this and then half on sports broadcasting. So the first half looks at the different wireless systems we've got out there. So when we think of what we've got different manufacturers like Shure, Trantec, Visicom, Audio-Technica, Sennheiser, and so on. I think we've got Sennheiser ones here today. And we've got growing differences in the directions that manufacturers take in terms of what we're using and what people think is the right thing or the next course of action as to what happens with UHF. So we've got, in terms of wireless systems, we've got UHF systems, digital over UHF, which is becoming increasingly common as we see, and we've got fully digital systems, and then we'll also briefly mention VHF systems, the things that have slowly found their way phased out, but partially by taxi drivers and all that sort of thing as well. So by UHF system, I'm referring to anything in the 470 to 865 megahertz bandwidth. So, and we're working on a full FM transmission. So the audio is modulated in a traditional FM thing there. And we see examples of systems that might be there, like we've got a Visicom and an Audio-Technica one there. More recently, companies like Audio-Technica have been bringing in and Shure, I think, as well, have brought in what's called high-density wireless that we see in other regions of the world. The 6000 series we see there, for example, we can use up to 31 channels in a 4 megahertz bandwidth. And we compare that to current, most normal UHF systems where we were lucky to achieve perhaps 5 in that same band. And that's down to what they say there as being IMD suppression, which is intermodular distortion. So whenever I think the best way of explaining this. So whenever we broadcast a channel or when we receive a channel, there's all this distortion created by frequencies that aren't the one that we're broadcasting, but they're harmonics of that, or they're additions or subtractions of that frequency, which will come into more detail as we go through the seminar. And by enabling us to suppress that, we're getting exactly the frequency you want, so we can fit more channels in without worrying about putting a channel in and it knocking 3 channels out, for example. So looking at traditional wireless system benefits of UHF, we end up with the best audio quality reliability versus reliability compromise, because for the most part, regardless of what we do to improve the range of the signal, the end result is still the same sound quality that we started with in the most cases. But as I was discussing with a few people before we came in, the increasing limitations on TV channels and selling different bands and all these things of, say, for example, 4G is working on 800 megahertz and 900 megahertz now, is increasingly limiting where we can put our channels. So all of those of us that used to use 863 to 865, it becomes increasingly less usable. And then U-band essentially which is our channel 38 band, even though that's a paid frequency, that's also becoming very crowded as well. And then another disadvantage is open FM broadcast. So for those of you that have used a digital over UHF system, some of the benefits of that are that they encrypt the signal. Because it's a digital signal, we can put AES encryption on that, which allows them, even though the broadcast is being done openly, it can only be collected by the receiver at any one time. Whereas in a traditional FM broadcast, we have to tell the customer that there is the theory that it can be intercepted in some way. Yeah, and then, like we mentioned, we've touched on briefly there, when we look at digital over UHF, we're thinking of the fact that we've got the possibility of a very high quality digital transmission, and we can do the encryption that I mentioned there. The problem with this is that most commonly, the systems that run this, if we put them on their highest audio quality, we end up with a very limited range on that. And in the case of a sports event, the key thing is reliability. And so in order to ensure that 110% reliability, they tend to have to put them onto the lower audio levels, and then we're left with a more compressed digital audio signal compared to our compressed analog audio signal that we had on the traditional UHF. So the perceived benefit becomes increasingly smaller compared to that. And then finally, for the most part, we see now is also fully digital systems which work on 2.4 gigahertz. So like we see there, our system 10, and in this case we have a two-way communication where they pair up. We don't have an open transmission, they just communicate one-to-one in both directions to share information. So as we see in terms of benefits, we're looking at, I just noticed what you meant about the parabola behind there. We were discussing before that there's a nice curve that puts sound right back into the microphone from there. That's quite cool. So in the case of 2.4, like our digital over UHF, we have the ability to transmit it as digital information. So instead of it being literally FM radio, we think about it being transmitted like WAV format, MP3, this sort of encoding and digital compression that allows us a higher quality of audio than we would have achieved with an analog broadcast. And in the case of things like churches and smaller projects, we don't have to get a license. We don't have to add that cost on. The customer doesn't feel like there's been a hidden cost at the end when they suddenly find they have to get charged for these extra bits that might not even get mentioned depending on the installers that go in for the project. The disadvantages become quite clear when you speak to people about 2.4 gig systems, is especially on their conception of digital wireless systems coming out. There was concerns about reliability in what's increasingly limited it. This only gets worse the more you go to shows like this, where we see camera systems working over 2.4. We see every single possible thing we want to make wireless tends to be over 2.4 and 5 gigs. So there is a concern to think about how many systems are we going to have. In the case of Audio-Technica, for example, we have to put things in place to ensure reliability over that. such as the fact that they're constantly changing channels, they're transmitting two sets of packets at the same time, because obviously on our data stream we can miss packets and eventually get them. But with audio, we miss a packet of data and we lose a second of audio, things that we'll notice immediately. So we have to do a lot more effort to make sure it's fine, and sometimes we might have to decide maybe it's not right for that, for example. Or if we need higher quantities of wireless, then we need to look at a different solution, a UHF. And like we see there, in most cases with 2.4 gig systems, the topology is quite limited. So they suit things like churches and classrooms quite well, where we just put the box in, set it up, and it works. But when we look at things like larger areas, or areas where we need to integrate multiple antennas for one microphone, like say a museum, someone walking around with a microphone, that's not something we could achieve with most wireless systems, if any, on the market that are digital. And I felt the need to put this VHF in, lest we forget about it, because I'm pretty sure there's plenty of installs out there that are still using plenty of Audio-Technica VHF systems that have stood the test of time to this day. I know I get plenty of calls about them still. And in the case of VHF, because the band is a lower frequency, we have a higher wavelength. And so we get a longer range as a result of that. Because the wave, if the wave is literally larger than the thing it's trying to get across, let's say a house or a human, then it's going to travel further. And that, on the flip side, that was the problem with our 2.4 gig systems in terms of range, is that 2.4 doesn't get over anything. So it can bounce off walls and reflections and fill a room quite well, but it can't go through the wall very well. So we had a longer range. I think we had this discussion about football pitches being able to use one VHF system and it be picked up everywhere in the local area. Our problems with VHF became clear in that everything was running on VHF. There was a two-way comms and taxis and all these different long-range communications all tended to be on VHF, which meant that it was overcrowded for use of multiple systems. And in terms of actually the technology of how the audio is modulated onto the wave, because of the lower frequency, the signal ends up being more compressed as a result of that. So VHF can't sound as good as a UHF system. So before I go on to our sports example, our broadcasting event example, I thought that there's some common terms that we get a lot of questions about. In terms of me being a product specialist, I get a lot of I'm the one at the end of the phone when you ring. Me and the 5 other guys are the people that, when you call up with a problem or a system, we're the ones that answer the call. So one of them, the common ones, is the fact of why we have 2 antennas on the back. So in terms of, we call that antenna diversity. We see the word diversity get thrown about by every wireless manufacturer. It essentially comes down to being any form of data where, It's any form where we've made a redundancy factor to enable reliability. In the case of antenna diversity, we quite simply have the 2 antennas on the rear. And the thought might be, well, we had another antenna, we make it more reliable. Because we've got 2, that must be better than 1. It's not quite like that. So the fact is, if we had 1 antenna on the back of our wireless system, there's the idea that if we, depending on the position of the antenna, that 1 antenna could pick up the direct signal and a reflection that's exactly out of phase with it at the same time. So the resultant frequency that we get from that is 0. And obviously that's only, it could be completely out of phase or it could be slightly out of phase, and it's still going to have an effect on the quality of signal. But the second antenna that we see there, the second antenna will always have a different phase relationship based on its location compared to the first one. So if one antenna is ever knocked out by that, the second one isn't. And that's why we have that, is to maintain signal reliability regardless of what signals are received on the antenna. There's also something that Audio-Technica has a lot as a feature called true diversity. And as we see there, this mainly comes down to its circuit. So on a more entry-level system, we'll find something called switching diversity, where the audio is, we have 1 antenna is processed, as we see there. And then at the very end, it's decided whether or not the antenna should be switched for a stronger signal on the second antenna, and then the process repeats itself. So in that case, there is always at some point the possibility that the audio could degrade momentarily. Whereas with true diversity that you see on our 4000 and 5000 systems that were recently renewed, we see that we have literally double the amount of circuitry inbuilt because the whole process is occurring twice, and the best audio is selected at the end. So, and we start to get an idea about why the cost goes up when we go up the chain in wireless systems, because in the case of that, we compare an AT 2000, 3000 series system to the true diversity of the 4000 and 5000, and the cost has literally gone up by almost double, and that's because internally we have twice as much going on. Right, so the next of our terms is intermodulation. So this is the common thing that we say when we find out someone wants 20 wireless systems and you say that'll be difficult for this or that, or people just put their own frequencies in and then find they have problems. The more units we put into a system, the more we're going to experience those problems. And it's all down to the way that our frequencies add together when we use multiples of wireless systems. It's exactly why we can't just... We at Audio-Technica always recommend that if you've got more than 10, 15 wireless, just give us a call. We give you a plot that we know works for your area and postcode, and then things should just work as they are. And if they don't, then you can ring back. We have the discussions of why they don't, as opposed to chasing tails as to what might be causing issues in certain situations. So here's our example of what intermodulation refers to: any frequency created by the addition of other frequencies in the air. So in this case, we have our actual transmitted frequency of 802 and 803, and then I have harmonics that come out of that, like any frequency, guitar string, anything that creates a note creates harmonics along with that, and these can all add together and subtract together. Every time we get a plus sum, the actual power of that frequency is double our original. So we can see why these intermodulations start to create problems for us. So in this case, we have our first set, and then we have a second set, and then what we find here is that if we carry along this chain, we end up creating two harmonic, just from having two channels of wireless, we've created two channels, two frequencies worth of intermodulations right next to the two we've got. So if we try to add on any of those channels, they'll just not work straight out the box. We've only used two systems. and we talk about using 10, 20, 50 wireless systems in a row. We already used two, and we start to generate the problem of what happens here. So it just goes on that the more we add, we get exponentially more intermodulations created. So literally, the more frequencies we use, the harder it is to get more into the system, which is why we end up looking at things like high density wireless as a possible solution to that, trying to reduce the amount trying to reduce the way that intermodulation affects our wireless systems. So here's an example that, say we have a pub or a nightclub that has two wireless systems currently. They want us to add one more in, so we buy them a wireless system, and then we take it in and we turn on the scan function to select. So that unit will just automatically select a frequency that's not one of the other two, and hopefully we should just be able to leave that and go. So let's take this example where we have two systems running on 802 and 804, and turn our scan function on our new system. Oh, there's our intermods from our two systems that we're running. So it sees that it can't use that, sees that it can't use those, but it can use 803 because the scan function says that's clear, there's no problem, no interference on that signal. However, now, once we do that, it knocks the other two out due to the intermodulations created by that, literally making 803 and 802 and 804. So the scan function should be used in these events, but we have to be quite careful about what we do with them, because the wireless system did what it was supposed to do. It found a clear channel and entered it. But in doing so, it can't know how it's going to affect that region. So it's just to have a bit of care when we do that. So the next of these terms is squelch. So commonly, it's one of the things that we'll fiddle with on the back of the wireless system when it's not working right, to see if we can try and improve the reliability here. Squelch literally just refers to the point at which it stops accepting signal. So imagine a gate opening and closing depending on how much signal enters it, literally acting like a noise gate. And so lowering this can increase the range of our transmitter, but then we start to add the possibility of having noise there. So if we see in our image here, our interference may be above the threshold to open the gate, and so we could turn it up to that. But obviously if our transmitter isn't loud enough, we can cut that out as well. This tends to be the result of that, and as sometimes I always hear it from churches most of all, where they'll say, oh, there was this really, really loud noise come through the PA and the wireless system, so we just turned it off, and we don't use that now because we're worried about it. And it tends to be the result of a wireless frequency that it doesn't know how to translate being received by the system as interference. And so the lower we make that squelch setting, the more likely that is to occur. So we always want it to be on the highest possible setting unless we turn it down. So we can use it to increase a bit of range with the warning that it becomes more possible to incur issues. Yeah, so we come to our last one, which we might come across called compander, which we find predominantly in traditional UHF systems. So, and this, for those of us that will know, compander is a compressor and expander, and in the case of a wireless system, they have to be pretty much perfectly matched as doing the compression at the transmitter side to then send the transmission to then expand it in a matching reverse of that to work. So we also have something called dual compander. So in the case of anyone who's compressed any signal ever, will know that if it's, say, a broad range, the low end energy tends to affect the compressor in a way we don't want it to. So a lot of the time we might end up filtering that out, for example, to get something that we think sounds like what we want to hear at the other end of it. So in the case of a lower end wireless system, because they have the single compander, that is exactly what would happen. There would be a certain loss of low end to ensure that the overall compression and expansion at the other end sounds relatively similar to what we're hearing already. In the case of this, having a dual compander means that we can split off the low end content so the compressor gets to act more naturally on both sides. And compared to any other wireless system, if you use a dual compander one, you will get more low end. Obviously, digital notwithstanding, but any UHF system will sound better that way. Okay. Cool, so that's most of what our discussion about the different systems that go on there. So now we come on to our wireless and broadcasting event. So in this case, we're looking at the event that we do in the Winter Games that's the most wireless heavy, which is the curling. I'm not sure if I was to guess which one is the most problems for us as an event, it would be curling, but as it turns out, that does tend to be it. When we find any of these events in the Winter Games, we speak about ice hockey, curling, the skiing and all that sort of thing as well. Or in case of us, as we're focusing on wireless, we're having a look at this example. Here we have a diagram showing some of the fixed point microphones in use for that event. The middle ones we see all in the center are all hanging microphones. This doesn't include all the camera mics that we might have there, for example, as well. As you might imagine, anyone who's done a larger tender would know that there's about 50 more of these PDFs on CAD documents, all with different things, even just ones showing certain cabling routes and so on. In the first place, it's quite simple in terms of the first thing that we want to do, is we just want to find out how many wireless we need, what we're actually needing to do there. So, bear with me. So what do we want to hear and where do we need to hear them? So in this case, we might think about listing what sounds we likely want to hear. So in our case, the guy comes back who does the broadcast, who knows exactly what we want to hear when we get there, says we want maybe the speech between the athletes, we want to hear the coach talking to the athletes between them. In the case of curling, there's only so much we can listen to, and people do want to hear the discussions and the random noises that they seem to make when they throw the stone and whatnot down the ice. And we want to hear the referee. We want to hear the sound of the stone following across the entire of the track, the sweeping action in the same areas, a low-end impact of the stones hitting each other. You wouldn't believe how specific these things get in these events, how they want to hear certain sounds of hooves on horse-related things, or they want to hear scrapings at certain points, or certain audience reactions and so on. And we also will want audio that's more relevant to each camera point as well, so that we can mix to those different stations. And of course, we're now in the age where everything needs to be surround sound, so we have to think about all the multiples of mics we need to make sure that we can get a surround sound image from that as well. And so in terms of our job now, all we need to decide is which needs to be wireless. And in our case, this one's relatively simple. We don't have to put any wireless systems in inflatable pelly cases or anything to put them in the sea. In this case, we just have to wire up all our belt packs to people. So how many do we have there? So per team we've got 4, so that's 8. And another coach for each team, that's 10. And then 1 referee, so that's 11. So we look there, and we see our full list again. So how many do we need to mic up? We said 11. Now, as it turns out, we have to run 4 curling events at the same time all day. So we now have to times the whole thing by 4. So we now need 44 systems. So it suddenly went from not being that complicated to suddenly we need a very, very large quantity to work out in that section. And don't forget we need redundant signals as well. So now we need at least 50 systems to ensure that we have enough systems plus reliability across the whole thing. So in terms of the frequency allocation, this is the big thing that's the stumbling block for a lot of systems, and it's the thing that makes or break the reliability factor on here. So obviously this begins with us going to the local authorities and finding out exactly which frequencies we're allowed. And then if we're not allowed the ones we need, we have an argument for 6 months or so. And then we finally get the ones that we do need for that, with certain caveats. What's really key and what doesn't tend to happen just because of the price point of wireless in a lot of situations is people don't go to the actual place to do wireless tests when we get there. And it's that difference so we at Audio-Technica can look at the local area. I can go on Ofcom and find out on the postcode what frequencies we can use in that area. But then we sell you 10 wireless systems and they get there and there's a problem. And we determine it's something to do with the frequencies, and an on-site analysis would show, there's someone illegally operating certain frequencies. Not many people want to pay the licensing fees, and a lot of people will very commonly just sort of let the customer worry about that, or maybe not even mention it during the installation because that's the customer's problem to deal with. So and not only that, but we have to remember we've got 4G, other networks, TV frequencies going on. As we said, that can be in 800 megahertz and 900 megahertz. We have the possibility that frequencies can be generated from those other broadcasts at higher frequencies that can end up creating intermods in that area that affect our channels as well. All of which is solved by doing an on-site wireless analysis. And that way, it sort of protects you as well, because you've sold the right thing to the customer, and we've turned up and found exactly the things that are going on. We haven't just trusted the accurate reports, we've also checked everything else. And then on another point of pragmaticism, if we decided that you wanted to sell them 863 to 865, so the free band, or channel 38, that's the only way of checking that. The only way of checking if another company is using channel 38 is by being there and doing the test. As that's a shared band, PMSE can't regulate that particular band by region. And like I said at the start of the session, most manufacturers either offer software for this, so you could get, if you got our 5000 series, we have a software package that lets you coordinate multiples of frequencies, or in in our case, just email us. If you're going to use our systems and using more than 10 or 12, just email us and we'll give you a plot. And it's obviously always better if you tell us before you've sold it to the customer, so that we don't have to find out that, oh, by the way, you need to return all of that because it's not the right band and so on. If you email us, we've got packages available to us to just create an intermodulation-free plot for you. And then we can say as a manufacturer that you've got exactly the right thing there. That we like to think that at every step, if you're supported, then you can blame us if there's a problem, which is how we'd prefer it to be. If there's going to be a problem, we'd rather it be a manufacturing problem or some kind of thing that we can cure, as opposed to chasing tails that frequencies weren't allocated or wiring isn't quite right, and so on and so forth. So don't always feel free to contact us with these things. So when we say on-site analysis, we have the fact that we look at actually the venue to see about where the wireless is going to go, is there things that are going to block it, is there local systems running on wireless that's time dependent. So that could be security guards using very loud UHF two-way transmitters that only come on when they talk to each other and then blow out a channel of your wireless during an event, for example. Things that have definitely happened to us in high importance events before. And there's a lot of time-sensitive things that go on, including mobile phone broadcasts might not always use a repeater station, for example. So if it's high-profile projects that we do, it is worth doing multiple times to go there. If we're talking about a lot of money, these things are worth doing. So, and like we see there, we have our images where we've gone to actually assess the building to make sure of any things that might cause any sort of connection issues for the systems. There's an example of the result of our tests there. It's a little bit hazy on there, but we see that for the most part, the areas that we were intending on using were around the 700 megahertz mark, and we find that we have very low interference there. And in other regions, and it's only until we get to the mid 900 that we get into a problem. And we see a very strong signal there that is on both of those, that is mobile phone masts. So from that we take that we have to be careful of using that area because they may use more bandwidth at certain points, and obviously that's always going to be too much signal for us to compete with using our wireless systems. Yeah, and in our case as well, in this particular event, we found that even though an area was clear, so speaking about the fact that things are time sensitive, we actually found that one of the free zones, when we asked the government for that time, they said, well, actually there's an early warning system that goes out on that channel if there's an emergency. So you probably can use it, but we don't want to give you it out of the fear that if something does happen, that transmission might interfere with ours. For example. There we go. So in our case, we took the software that we used along with the availability that we had and ended up with this chart here. So this, not only did we just make a plot in order to get that channel count there, but we also had to make plots that directly didn't interfere with the other events local to that region. So not just all the other things we've mentioned, but also if we have multiple events going on, or multiple matches, or other broadcasters using wireless for their own purposes, we have to make sure everyone's on the channels that they have to be on. We were quite fortunate that we have our high-density wireless systems. As we see there, we fit an awful lot into one channel band. Now, a thing I didn't mention as a disadvantage of our high-density wireless is that we can get 31 channels in that 4 megahertz band, but we have to buy a unit that's 4 megahertz. So that's where the element of how high profile is the project for that. Because if we can afford to get it to buy the systems in for that one particular event, then that's fine. But if we're hiring that stock out, there's every chance that a 4 megahertz band just isn't going to be available, especially in England. We'd have that problem. So in our case, we could utilize that and get these high channel counts in there. So as we see there, we've got 6,000 for the most part, apart from at the very end, some transmitters from our 5,000 series as well. Now, they were just, as we can see, they were just used as backup. The order that they're in now is the order that we used in. So the very last ones were all backup frequencies. And we left the 5000 as backup, not just for our sake, but because of the size of the transmitters. So some of the feedback we got was that the belt packs were too big on our 5000 series. So using the 6000 instead meant that we could implement ones that made the athletes a little bit more comfortable with that. And when you think that they have to wear that for the whole time that they're doing something like hockey, for example, not just curling or slower sports, it starts to make a difference, the size that we have there. So we go on to the actual installation now. And our key point is obviously wiring. In high-profile events, we'll have multiple documents all stipulating the different areas that wiring goes, the different areas that things are arranged in, the documents showing exactly where everything should be in the actual venue and so on, and what the signal path is as well. And we obviously have our drawings showing the different cabling going on that. It sounds like an obvious thing to say, and we seem to hear it a lot, but I still see it now of people not wiring in the way that we ought to do. Quite simply, that tends to be putting power with other things. So it seems really obvious, but it's the easiest way of creating interference and problems with your signal is by taping our RF cable to a power cable. So it is worth remembering that we should always be separating the power and the audio. We all know it, but we all forget about it, or installers who are rushing to do a project might not consider it, but it can create a big issue with connections. And it's just simple things like that can cost us a lot of time where we could have avoided it. So in terms of the antenna placement, so before we discussed that having two antennas is good, they're always on a different phase relationship because they're in different positions, so that means that they're more reliable because of this difference in phase relationship. But when we get to actually place larger antennas, like our dipole antennas there, our paddles, there are actually better positions for spacing them. Now this is something that we see a lot where people might just decide to put one in one room, one in the other. And obviously we don't recommend that because that's not diversity. They're a completely different position. But how near in the range of a meter they can be makes quite a lot of difference. So in this case we see if we actually space them a full wavelength apart, so if we were running in around channel 38 sort of region at 600 megahertz, we find that that's a half a meter apart, then they're both receiving exactly the same direct phase relationship. So there's no benefit to that in doing that. Not as much as there would have been, as there could be, as we'll see. So thinking about it in an opposite way, if we position them half a meter away, they're exactly out of phase, which gives us the opposite problem. So what we actually get to is that if we position them a quarter wave or any odd multiple of a quarter, then they're always, then when one is at its 0 point in the wave, the other one is getting full signal, always. So that's a really simple thing that we never really consider. We just put the antennas in and get them spaced. But if we take so say we've got 4 frequencies, we take the average frequency from those 4, like the one that would be right in the middle, and then actually measure out say 3/4 of a wave, we can improve the reliability of the antennas there. So we make the best use out of our antennas there. Yeah, so as we see, we'd always calculate a quarter and then just, in my case, I always put them 3/4 of a wavelength apart. And then that way we get the best possible diversity from our antennas at any one time. So boosters, obviously a lot of the things I've covered today are very short versions of what's a long conversation. I'm very happy to have a lot of those long conversations. Boosters is one of them. We can go into boosters for an entire session on its own, so I wouldn't want to do to anyone. And in the case, the simple things that we have here is when we're actually using a booster in a situation, we're mainly using it to either increase our operating distance, or we're using it to push us above some kind of interference issue in reception. So the best thing we can do for using a booster is if we have multiple boosters, don't put them along each part of the cable joining up. If we put them right at the antenna, we get the most signal to noise. So even if you've got 3 in a chain, always put them as near to the thing as possible. And that may be using short runs of cable there to then have one long run of cable later. And it just means you're boosting all the signal with the lowest amount of noise there as well. And then it's just keeping in mind that when we use a booster, we also increase the minimum distance from the receiver to the transmitter. So if we've got an antenna and then a booster, we now can't stand as close to that antenna as before. So we just have to make sure that we have a minimum distance from them. If we're not sure what that is, again, we have ways of calculating that for you, so we can tell you whether you've caused an issue there. So say with the paddle antennas that we saw, adding a 3 dB boost there could increase the minimum distance up to about 7 or 8 meters, which in the case, if we put the antennas on a stage, suddenly that's half our stage that we've lost signal from. Okay, cool. So that we can get, we're nearly done now anyway, so excellent. So in this particular event, we use boosters, like I said, to boost above the potential of interference from a TV channel that we saw on the report that was operating close by to what we were using. So as we've sort of talked in that last segment, we can look at some of the practical things that we should take away from this event. So when we're actually looking to coordinate the frequencies, we find out how many we need. We look up the postcode on PMSE Ofcom. So if you search that on Google, it'll come up with the page that you can register with, and you can put your postcode in to check that. Obviously, if you're in a different country, it's a different regulation. I think Ireland's included in that, but it's a different area. And we can use that, and then use if we've got a couple of systems, we can use the scanner there for a small amount, but it should always be backed up by a wireless check, by going and actually doing an RF analysis in the area. Particularly if it's an area where they've previously experienced problems, and that's exactly why they're replacing the wireless system in the first place, because it could be a problem with RF in the region that's causing the fault, and not the fault of a receiver and transmitter. Like we said, if we add further systems, we probably need a new, to a place that's already got systems, we probably need a new frequency plot entirely. It's not likely that we'll just be able to add on, unless we already made a plot that was bigger than that. And like we say, always feel free to contact the manufacturer, because we'll be happy to give you a wireless plot there. And finally, we said with our installation aspects, calculating the spacing for antennas can make a big difference to the benefits we can have by running them. We do want to, what I had mentioned before, is it is worth obviously putting antennas above humans, because they absorb RF in themselves. So especially with 2.4 gig, it's pretty imperative that we can get the systems above people, because we absorb it pretty badly in our own way. And then with boosters, the main things we have to be careful is overloading the signal, things that your manufacturer can help to define with you. And we always want to place them at the very beginning of the chain, because otherwise, if we put them at the other end, we're boosting noise as much as we're boosting signal. Okay, so like I said, that was very much a glimpse of a lot of aspects that we can get into all separate seminars in themselves. And so if you have any questions at all, you can feel free to ask me now or afterwards. I'm at the AT stand. And I'll also, for those of you that might want to speak to me afterwards, I can give you my card, and we can follow it up with the discussions after as well. So,
yes, so if you're in the room, if you want to ask questions now, in the session, we've got 5 minutes. Okay. But if, as you say, if you want to have a longer chat with Matthew, you can do that on the Audio-Technica booth. We will be serving tea and coffee again in the marquee, so please go back there. Everyone's welcome to see you. I know some of you probably might want to be getting away, but go and have a quick cup of tea and a coffee and a chat first. But we'd like to have a big thank you to Matthew for his presentation. Does anyone have any questions they'd like to ask now? Okay.
Just a quick one about how you manage synchronization of the audio and video and latency across the different transmissions.
Okay, so in terms of UHF, you don't really experience a latency. But like you say, with the digital, I'm pretty sure most digital and digital over UHF have about 4 milliseconds of latency. And I think that tends to be why you don't see like monitoring systems running digital, because that latency is we start to put things into a DSP, the DSP has latency, and it all adds up. But in terms of actual, like we found there, in terms of the actual broadcasting situations, they're nearly always running analog UHF. So latency is never comes into it. But it's an interesting one, definitely.
On the winter and summer games events, the synchronisation's all done in the OB bands, and then it's sent off together to the main. They usually have OBS place, which then goes and split into all of the broadcasters, which then goes back from the broadcasters like the BBC or NBC, and that then goes to the satellites. But the synchronisation of video to audio is done in the OB bands on the site. Yeah.
And you don't tend to find that the actual audio, I guess, creation device, as it were, as word clocks or anything like that. That always tends to be on the device that's got the preamps and the actual mixing units afterwards, where word clocks and synchronization starts to come into play. Obviously, a lot of that can come down to, when it's pure audio, it can come down to actual input delays and so on. But as Logan says, it's all done further on down the chain, as it were. So, cool. Anyone else? Yeah?
Let's ask about the antenna spacing you said. Doesn't their effective separation depend on the direction that the radio wave arrives from? And so if the transmitter is moving with respect to the antennas, how do you figure out the optimal spacing? Well,
the spacing is just based on the actual transmission, so that it's a bit of a long discussion in itself. Maybe we should talk about that after, perhaps.
Okay, sure.
It gets more and more interesting as you go into it. Essentially it comes down to that, because you can deal with it, because UHF is this frequency that we can actually space openly, having typically the time it takes to get there is always the same. In terms of the transmitter to receiver is always the same in terms of how long the frequency takes to get there. And it'll tend to be the reflections where the phase can change. So in this case, we're just talking about how what their relationship is when the same frequency hits both antennas, as opposed to a reflection or anything like that. Does that make sense?
Well, I was just thinking, if I had antennas here and here, and you were the transmitter, then however far apart they were, they'd be in phase.
Yeah, they'd receive the same. They would receive the same signal, but it's complicated. Okay. But we can have a little chat about that after.
All right, sure.
Yeah.
Yes, so I would encourage you to have a chat with Matthew back in the marquee. He can spend as much time with you as you want. So once again, thank you, Matthew.
No problem. Thank you very much.